Someone has requested that I do look at this very important concept in chemistry, and what I'm going to look at today is the balancing of chemical equations. I'll be able to use few chemical equations to be able to explain the concept behind how these chemical equations get balanced. And the first chemical reaction that I'm going to use is a reaction between a metal and a non-metal. So I have expected that a metal ends up reacting with a non-metal, and what you're supposed to notice this: when a metal reacts, the metal loses. So the metal loses and the non-metal gains. And you're always told that when a metal loses, it ends up forming a cation. And possibly everyone knows that a cation is a positively charged particle for that matter. And when a non-metal gains, it forms an anion, and an anion is a negatively charged particle. And at the end of the day, the positively charged metal acting as a cation strongly gets attracted to the negatively charged non-metal referred as ion, and they'll end up forming a very strong bond called an ionic bond or an electrovalent bond. So the bond getting formed between these two different particles with the different charges is called an anionic bond or an electrovalent bond. And we are not going to look at bonding and structure. We are going to look at the part that I have been asked to look at, and that is balancing of these chemical equations. And I would want to use this example. If magnesium as a metal reacts with nitrogen as a non-metal, preferably a diatomic gas, and of course a diatomic gas is a gas that has to actually end up getting its structure consisting of two atoms, of course, of the same element. I'll have magnesium as a solid strongly reacting with nitrogen as a gas, and they'll be able to give me a product which is magnesium nitride. And this is the chemical formula of magnesium nitride. How then do we end up getting this product? For example, I'll take magnesium and nitrogen as separate elements, and I know magnesium is an element in the periodic table, which is a metal found in group 2 that has an atomic number of 12, and nitrogen as a non-metal is found in the periodic table occupying a position with an atomic number which is 7. So the electron configuration or the electron arrangement of magnesium is 2 to 8 to 2, and the electron arrangement of nitrogen is 2 to 5. On reacting, magnesium ends up losing 2 outermost electrons to form a cation. So it forms a cation, and nitrogen ends up gaining 3 electrons to form an anion. So we shall have 3 negative. So these are called oxidation numbers. And of course these oxidation numbers are going to actually end up getting interchanged for us to form the product. And that means the 3 can drop to this end and the 2 drops to this other end. We shall have magnesium nitride getting written like this. So it is a nitride, N-I-T-R-I-D. So that is magnesium nitride. So we want to see how we can be able to balance this equation. It is always advisable that you look at the one that you think you can easily balance in terms of any element or atom in that compound. For example, if I begin from this end, I have only 1 atom of magnesium, but on the product side, there are 3 atoms of magnesium. So that means to balance the atoms of magnesium on either side of this reaction, I'm going to actually put 3 as a coefficient of magnesium, and that means I will have 3 atoms of magnesium well balancing with 3 atoms of magnesium on this other side, now the product side. If I get back to the second part of the reactant, which is nitrogen, I have 2 atoms of nitrogen that form a diatomic gas called nitrogen gas, and on the other hand I still have 2 atoms of nitrogen, and that ends up giving me a balanced chemical equation for that matter, and this is a white solid, and that is how we can be able to balance this chemical equation. Another example that I can use to show that the reaction can actually get well balanced, I'll be able to use aluminium and chlorine as a gas as well, and when these two react, I do expect to find this as my product, aluminium 3 chloride. Look at that. So then how do we even end up getting this as our product? I definitely know that if I take this as aluminium and take this as chlorine, I know aluminium has an atomic number of 13. So its electron arrangement is 2 to 8 to 3. And chlorine has an atomic number of 17. So the atomic number can actually get used to determine the electron configuration. So we have an arrangement of 2 to 8 to 7. Definitely, I think you know this. This is a metal, it is going to lose. So it will end up losing 3 electrons. So it will develop what you call a positive charge. That will be a cation. Then chlorine is going to gain 1. So it develops a negatively charged particle. And that means it ends up becoming an anion. So definitely, on interchanging the oxidation numbers, I'll be able to get aluminium 3 chloride getting written like this. And you'd want to know, when do I know that this element is going to lose and it is going to gain? Let's look at this scale that I've always shown my students. I'll actually say 1, 2, 3, then 4, 5, 6, 7. I won't even involve 8 because those that have 8 electrons in the outermost energy level are stable. And a good example can be the noble gases or the rare gases or the inert gases or the group O or the group 8 elements in the periodic table. So we shall focus more on these other parts of this arrangement. So if I decide to actually made this, I realized that whoever came up with this thing had actually put this in mind, that if an element has 1, 2, 3 in the outermost energy level, then that means it is going to lose. And on losing, it develops a positively charged particle and it has to be a metal. So if I have 1, 2, 3 in the outermost energy level, these ones I'm actually going to take them as valence electrons. So there's a difference between valence and valency. And someone knows that valency and valence can interchangeably become confused. And you'll actually realize that the first one refers to how many electrons an atom can lose or gain to become stable. And the second one refers to the number of electrons in the outermost energy level in any electron arrangement. So the first one is valency, to refer to the number of electrons or electron that an atom is going to lose or gain to become stable. It is also called the combining power of an element. And valence, the second one with an E at the end, refers to the outermost number of electrons in an electron arrangement of an element. And if you come back here, we are actually taking these ones as valence. So if I find 1 electron in the outermost energy level in an electron arrangement of an element, that element is going to lose. It must form a cation. It must be a metal. If it has 2, it still loses. It will form a cation, and it is actually a metal as well. If it has 3, it will still lose. It will be a metal, and it will form a cation. If it has 5, 6, 7 in the outermost energy level, in terms of that arrangement, it is going to form what you call an anion, and it must be a non-metal, and it must be able to form an anion by losing, no, by gaining. Correct. So, and then it is very easy for me to know that this element is going to lose or gain, and as well know that this is a metal or a non-metal based on what happens to that element. If it will either lose or it will actually be able to gain. Now we want to balance this. Aluminium has only 1 atom, so it is well sorted. This other side has also 1 atom of aluminium. If you look at chlorine, it has 2 atoms. This chlorine has 3 atoms. So chlorine is not balanced. I would advise students that finding yourself in such a scenario will demand that you actually take the odd number, isn't it? And use it to actually make it become an even number. So how? I know this has 2 and this has 3. So how do I even balance this equation? I'll take this 3 and put it here. I just interchange those values. Whatever has to actually get written here should come from this end. And whatever appears here should come to this other end. You just interchange those values. You see? So aluminium had 1 atom initially. Aluminium as well had an atom on this other side of the equal sign, or actually the product side. And chlorine had 3 atoms on this end and then 2 atoms on this end. 2 different numbers. So what do? We'll take 3 and put it here, then take 2 and then put it here. That can equally be able to balance the atoms of chlorine. So 3 times 2, that gives us 6. Then here we have 2 times 3, that gives us still 6. Aluminium has actually been able to get interfered with. We have now had 2 atoms of aluminium, and yet on this side we have only 1 atom of aluminium. How do we even balance this? We shall put 2 on this end to balance this very important part of this reaction or this chemical equation. And this is aluminium, which is a metal. So that equation is well balanced. Please remember to write the state symbols. This is a solid, this is a gas, and this is a solid. It's a white solid. So this is a very, very, very easier way of doing this. I would definitely be able to look at maybe a metal reacting with oxygen gas. Let's say sodium reacts with oxygen gas. And what do we form? So I know very well you have been told this in your studies, that when a metal reacts with oxygen, it will definitely form what you call a metal oxide. So a metal plus oxygen is a metal oxide. So sodium plus oxygen, sodium oxide. And this is the formula of sodium oxide. How do I even end up coming up with this equation and this formula of this product? I'll come here and then say, I have sodium, then I have oxygen. I know sodium is number 11, so the atomic number is 11, and oxygen is number 8 in terms of its atomic number. So the arrangement here is 2 to 8 to what? To 1. And the arrangement here is 2 to 6. So this has 1 electron, the valence is 1. Based on this scale, it is going to lose. It will form a cation, so it loses 1. Correct. This is 6 as the valence. Based on this scale, with 6, it is going to gain. So you have to ask yourself, it has 6. How many is it supposed to gain for it to actually develop what you call an octet state, where it will end up having 8 electrons in the outermost energy level. So it will end up gaining 2 more electrons, so 2 negative. So it develops a negative state. When you're changing these values, I'm going to have these 2 dropping here. You can't even drop 1. So you'll have sodium oxide getting written like this. So to balance the equation, let's ask ourselves, sodium has 1 atom, and here sodium has 2 atoms. So to balance the equation, I'll put here 2. So sodium is balanced. Let's get to oxygen. How many atoms? 2. And here, 1. So I definitely be able to come here and then put, now you know, if you want to balance oxygen, you can't put 2 at the bottom here. Doesn't even work. So what do? You'll be able to actually put just behind this compound. You know, it's going to serve as a coefficient for the whole compound. So you'll be able to put here 2. So that now the atoms of oxygen can actually end up also becoming 2. So these 2 can be able to multiply all through the equation. So 2 times O, which is 1, so we have 2 atoms of oxygen. Then 2 atoms of oxygen as well. How many atoms of sodium? 4 now in this case. So we shall be able to change this to 4. That's why it's always advisable to use a pencil when balancing, so that you can be able to make changes where necessary during the balancing process. I'll maybe look at 2 more examples, then I can be able to end my class for today. I can decide to end up taking maybe a metal reacting with an acid. And I obviously know when you react a metal with an acid, you're going to get. So let me first write the state symbols of this first initial equation. This is a solid, this is a gas, and this is a solid. The state symbols must be written for chemical equation to make meaning to any scientist. So I'll realize that when a metal reacts with an acid, I'll be able to get salt and hydrogen gas. Correct. So let's get back to this. I'll say, for example, potassium plus sulfuric 6 acid. And they always advised that when acids are getting reacted with metals, they should be in their dilute form, so that the rate of reaction is slowed down to prevent any vigorous or explosive reaction that might actually endanger the lives of anyone doing this chemical reaction or chemical equation of this experiment. And we always advise students to avoid using these group 1 elements because their reactions with acids are very explosive. So for the purpose of just writing this chemical equation, then balancing the equation, I'll be able to get exempted from this and be able to use it just for today so that you can be able to balance the equation. So we shall be able to end up having now a metal part getting the last part of that acid. So it gives us potassium sulfate. And then we shall also produce a hydrogen gas. One observation to make is that there is effervescence. Why? You can be able to produce hydrogen gas in this case. And of course, this is an aqueous solution. Dilute acids are aqueous, and this is a solid, which is a metal, which is potassium. So the expectation of this reaction is that this is going to be a very vigorous reaction based on the metal we are going to use. It is a group 1 element. So, but again, we shall want to actually balance the equation. How did I even end up getting potassium sulfate? Get it written like this. We shall realize that potassium is a group 1 element, and its electron arrangement is 2 to 8 to 8 to 1 because it has an atomic number of 19. Of course, the atomic number is the same as the number of protons, which you can be able to actually get as well. Getting used to write the electron arrangement, the electron configuration. We can now be able to realize that it actually has 1 electron, the valence, which is 1. It can be able to lose 1 electron to develop a positive charge, so we shall have a positive charge here. Then the sulfate as a radical. Remember, radical is a group of atoms that exist and react as a unit with a net charge. So this is a sulfate with a net charge of 2 negative. So if these 2 drops here, that's the formula of potassium sulfate, then plus hydrogen gas. So we have 2 atoms of potassium. So what do we do here on this other end? We shall put 2 here. Just ensure that that equation is well balanced. Then we shall now look at the next element, which is hydrogen. 2 atoms as well, 2 atoms. That is correct. We have 1 sulfur atom, 4 atoms of oxygen, 4 atoms of oxygen. So the equation is well balanced. So get me the next video for us to even get more examples based on what we are going to have in terms of balancing chemical equations when given in a particular examination. Have a nice day ahead.